this thing. Okay, so these are my two codes, right? This is the one in Arduino code. This is the one in register, right? Neither of those is the optimal way to code. They are just different ways, right? This, the right side, is the Arduino way. I write it in another way so I can explain something to you. So now you can learn different things, right? So these two things are the same for you, right? You have two functions, the setup, the loop, that's the same for everyone, right? Okay, then I have a for cycle. Anyone knows the for cycle? Okay, so for cycle runs any number of times. It runs if this condition is met, right? Every time it's met. And in this case, I declare a variable by. It means it's 8 bits, right? So it's a number of 8 bits. So I can count with this variable up to 255, right? I can count 256 values from 0 to 255. And I initialize the value with a 2, right? And this bar will be running every time this condition is met. And each time it runs, I will do this operation. I plus plus. I plus plus is the atomic way, atomic, to write I equals I plus 1, right? And I can also write I minus minus, like that, right? And this is heritage of C++, the programming language. It's called plus for this, right? For the atomic way to write. So in this first cycle, I will begin with I equals 2, and I will run all the things that are between the curly braces. In this case, I start with an if statement. So I am checking if this operation equals to 0. Anyone knows what's that operation? Module. It's called module. It's I percentage 2. It means I am dividing I over 2. And the module retrieves me the receipt of that operation, right? So in this first case, I equals to 2, right? I start with I equals to 2. 2 over 2 is 1. The residue is 0, right? This is the thing that this function is delivering, right? So now I check, is 0 equal to 0? Yes, right? 0 equals to 0. So I run this instruction. Pin mode 2. In this case, I is 2. It's blue because I have a button connected there, right? Is that clear? Okay, I run the H, I finish here, and now I increment I. Now I is 3, 3 module 2, 3 over 2. That's a 1, residue of 1. It's 1 equal to 0? No, okay. Else, pin mode 3, output, because I have an LED on 3, right? Then I got there 2. Now I equals to 4, 4 over 2, 2, residue 0. Okay, pin 4 is an input. And then 5, output. 6, input. 7, output. So now I declare the pin modes for all the elements that I got there, right? And that's just a more compact way. And it's useful for me because I can explain both the for and the module operation, right? And any questions about that? Okay, perfect. Then in the loop, I got another for. Okay, in this case, I use another variable. I put the same. I just use another one, j. I start at 2, and this will run if j is less or equal 6, right? When j goes to 7, 8, whatever number, I will leave that part, right? And now my increment is j plus equals 2. J plus equals 2 is the atomic version of j equals j plus 2. That means that every cycle of 4, I will be incrementing the j 2 times, right? Okay, perfect. So I will start with 2. So digital write 2 plus 1, 3. I will be writing on 3. I have an LED there. My reading of the button that is in 2, right? So I read 2 and I write this value to 3, right? And I have this exclamation sign. And what does that mean? What's the meaning? It's a no. Yes. So if I read a 0, I change that to 1, and that's the thing I am writing, right? The reason for this is because I declare my buttons with pull-ups. That means that if I don't press the button, I will be reading a logic 1, right? So if I am not pressing and I don't have the NOT, I will have the LED turn on. And I want to turn on when I press it. That's the reason I negate that press. So now the button is activated, I negate, the LED is off. When I press it, it's on, I negate it, it's on, so the LED should turn on, right? I run that for LED 3 with button 2. Now J will be 4, right? Because I am by 2. And now I am putting to LED that is connected to 5, the reading of the button in 4. And I repeat the same for 7 and 6, right? And that's all the code that. Is that clear? Yes. Okay. What's this? Theta times equals 10. This thing. Theta times equals 10. C equals theta times 10, right? Is the atomic version for that. I can write the atomic version for divisions also, for subtraction, or whatever. It makes it easier to write a lot. Any questions? No? Okay, perfect. I told you that I don't let me write in the whiteboard. I need to write here. Sorry. Okay. Now, the code in the left. That's easier. Let me change my screen so I can write here. Here. I should be writing here. Okay, I got already the code here. This is the code with registers, right? Okay, so in this case, what is DDRD for? To declare if a pin is an input or an output, right? This one. 0 means input, and 1 output, 1 output, right? So this is pin 0, we are not using this, right? Pin 1, we are not using that. Pin 2, it's our bottom 1, right? Pin 0, 1, 2, 3, it's our first LED, right? Then our second button, second LED, third button, third LED, right? All the LEDs should be outputs, all the buttons should be inputs, right? Okay, so DDRD tell us is the data direction register. Tell us if it's an input or an output for the microcontroller. Then port D, what's port D for? Okay. Yes. If my bit is an input, in this case, this is an input, right? It's associated. If I got a 1, it means I want a pull-up in that input. If I put a 0, it means I don't want pull-up in that input, right? So for each input, I have to assign or not a pull-up, right? So that's for that, and this is for that, right? And if my bit is an output, in this case, this is an output, this is an output, and this is also an output, I write the value of the output. If I put a 1 here, this LED should turn on, right? In this case, I turn off 1, 2, the 3 LEDs are turned off, right? These other 2 numbers, I just put some numbers there, but they could have whatever value. Is that clear? Up to that point? Okay, perfect. That's the easy part because that's the same as the last class, right? That should be clear. Okay. Now, this is the code to turn on all the LEDs. It's just one line, okay? So the idea is the next, okay? We will start with pin D. What's pin D? Yes, it's the register that possesses all the values from the inputs, right? So in this case, the bit 7 is an input or an output? Pin 7, the register, the bit 7. It's an output, right? It's a LED. So that value doesn't matter, right? 6 is the bottom 3, right? The bottom 3 value, okay? I will put some lines there. Okay, next bit, it's an output, doesn't matter, right? Next bit is bottom 2. Next bit is our first LED, right?
our first LED, and then our first button, right? And the first two bits doesn't matter because we don't declare anything for them. Yes. So this thing is our PIND. Now I have this operation here. What's this? It's a not, a bitwise not, okay? A bitwise not is just negate all the bits. So if this bit is a 0, now it's a 1. If this bit was a 1, now it's a 0, right? So I will have not whatever thing I got there. I will put an X, right? It should be negated. Now, whatever thing I am reading in the bottom tree, now I should negate that, right? I am using the exclamation point because it's just one bit, right? If I want to negate all the bits, it's when I use the curly line, right? So this doesn't matter. Here I will have negate button 2. Does not matter. Negate button 3, button 1, sorry. And does not matter, right? This is the PIND negated, okay? You just have to flip all the bits. Here I do not flip the X's because I don't know their values, right? So it doesn't matter. Okay, now what is this part? What is this instruction for? Yes, this means move to the left. In this, the number of spaces, right? So I will move all the bits one space, right? It means that now I will have here not B3, right? In this position. I will have this X here. Here will be not B2. Here will be the X. Here will be not B1. Here will be the X. Here will be the X. And here I will have an unknown value, right? Because I shift X bits. This one, I don't know what's happening there, right? In the real life, it will be a 0, but we cannot be completely sure of that. So that's the reason I am putting like an interrogation mark. Okay, so this is PIND negated with one bit shift to the left. Okay. Why I'm doing this? Because now I read the bottom, right? I negate the value because remember I have the pull up. I want to change the behavior of all the bottoms, right? So right now I have all the behavior changed. Then I am sending the reading of this button to the LED, the reading of this button to the LED, the reading of this button to the LED, right? Because I am reading this to 4D. That 4D is the one that writes to the output, right? The problem now, if I am just making this thing, is that here, these are the bits for the pull-ups or not pull-ups in the inputs, right? So right now, I don't know what are the values there. So maybe I am quitting the pull-ups, right? That was the problem with one thing, right? That you told me, if I don't erase it, if they change, because you are changing between ones and zeros, these things every run. So that's the reason it was blinking, right? So the thing that I have to do is to make sure that these bits will be always ones, okay? How I am doing this? With this little mask, right? So I have my mask. My mask is 1 0 1 0, starting with 0, right? 0 1 0 1 0 1 0 1, right? And then I am doing an operation between these two things. So not B or 0. It's not B3, right? Everyone agrees on that? Because if you do an OR with a 0 and the other number is a 0, it remains a 0. If it's a 1, it remains a 1. So whatever is the value of not B3, it will remain, right? If you put here a 1, if X is 0, what will be the result? The result of 0 or 1? 1. And if it's a 1, 1 or 1? Also 1. So every time I got a 1 here, it will stay as a 1, right? So this will 1, this will be 1. This doesn't matter, but this will be 1, right? But does not matter. And here, the zeros let pass these things, right? So I will have here not B2, not B1, and whatever thing I got there, right? So with this mask, the only thing that I am doing is maintaining here the pull-up resistor. That's the reason I select here 1, because I want to maintain my pull-ups. And the zeros let pass whatever value I generate before, right? That is the signal of the buttons inverted, right? And with that code, it should work, right? You are having the problem because you have here an AND, right? And you are multiplying by zeros and by 1. I think that's the reason it was flipped, right? Now we already studied two types of masks, right? Or no? Yes, one with OR and one with ANDs, right? So let me write. For example, imagine that we have x7, x6. No, I don't have to do a lot of numbers. I will do it just 4, right? X4, x3, x2, x1. And here I want to put x4, x3, x2, x1. Yes? The first kind of mask is really easy. It's a mask with an AND operation, right? If I want to let pass 1 bit, for example, I want to let pass the x3 and I want to delete the other 2 values, what can I do there? If I put a 0, I will delete this one, right? If I put a 0 here, I will delete this one. If I put a 0 here, I will delete this one. If I put a 1 here, I let pass this thing, right? So I can make a mask, so I let pass whatever value I prefer, right? The other kind of mask that I can do is if I want to make an OR. I will put OR here. Well, I don't, right? In this case, for example, what happens if I make an OR like this? The same mask. What happens there? Are you sure? What I am doing there? This value, x4, it passed, right? And x2, pass. x1, pass. And x3, I am doing 1, right? So I can do the same, right? I can let pass just one value. For example, I will change this to this. 1, 0, 1, 1. And I am doing 1 here, x3, 1, 1, right? So I can let pass whatever value I want, and I can make that the other values are zeros or ones, depending of the thing that I want, right? And I can do a mask to let pass 1, 2, 3 numbers, right? It depends on the thing that you want to achieve, right? Yes. It will always be 1, right? And in the end, if you have a 0, it will always be 0. We are using those properties to let pass just the bits that you want, right? So maybe that's the one that I am interested in, right? Or maybe there are 2 and I can put another one there and let pass 2 bits, right? One example of these things is here. This is a code that is from another of your classmates from another group, right? And they deliver me this code. And this code, I am almost sure that is ChatGPT code, okay? And some of you deliver me something like this, okay? What's that? What does ampersand equals curly line means? Sorry? Yes, that's an atomic version. It's the same as the sum, the multiplication that we studied there, right? So this means DDRD, it's equal to DDRD and the thing that I have here, right? In this case, it's not 1 shift PD2, right? And another parenthesis. So it's atomic version. If I have the ampersand before, it means that The first element of the AND is this one, the second element is this one, and I will save that here. It's just as it is, right? In this case, what's the other thing important? Do you know what's PD2? PD2. Yes. In class, we already studied this one, right? I teach you this and this and this, but I never teach you PD2, right? Because it's not so normal. This is things that ChatGPT knows, right? This just means 2. This means 4. This means yes. In the port D, all the pins are called PD0, PD1. Okay? They have other names, other teams. I just learned this today because I don't know, every team delivers things different. This PD2 is the same, PD2. It's equal as DDRD2. Okay? PD3, DDRD3, PD4. Okay, and also it's the same as DDD2. But that's the same as 2. So please, if you can, use the direct way, right? Just use the 2 or the 3. That's easier for me, okay? That's the first time I see this. There are some things that ChatGPT knows that I don't know, okay? Now, okay, I am doing that operation, right? So let's suppose that DDRD, I don't know what's there, but it's what size? What's the size of DDRD? 8 bits, always, right? All the registers are 8 bits. So this is my initial value for DDRD. This is DDRD. Then I am doing an AND with this operation. So let's start with this. What's this? A 1, right? How many bits? 8 bits. So this is 0, 0, 0, 0, 0, 0, 0, 1, right? That's a 1. Then that thing, I am shifting PD2 to the left. So I am shifting 2 times to the left. That's the meaning, right? So 1, 2, it will be like that, right? 0, 0, 0, 0, 0. And this, I don't know what's there, right? And let's call this 1. I will put the 2, okay? We always know that. Okay, then this thing is a bitwise NOT. That means flip everything, right? So now, not 1, 2. Sorry, not like this, no? It's a NOT. Means now this is 1, 1, 1, 1, 1, 0. We don't know. Okay. Then I am doing, okay, now we got this part. We already know this, right? We have to do the AND between this and this thing, right? What's the result of that? What's whatever number and 1? Whatever number, right? It's the same for this, the same for this, the same for this, the same for this. What's whatever number and 0? 0. Okay, perfect. And here I will put whatever, right? Because we don't know what's happening. Okay, and this, we are saving that in DDRD. DDRD. So what do we do in this instruction? We start with this, right? Now is this thing what we achieve. Yes, because we have a button there, right? 0 are input. So all this code, just make that this bit is an input, right? Then this instruction is what? We have a 1, right? And we are shifting that 4 times, and we are negating that, right? Everyone's agreed on that. So I have 1, 1, 1. This is 1, 2, 3, 4. Okay. 0, 1, 1. No, sorry. Here we don't know, right? We don't know. Yes? That's all this part. Yes? I, yes, I did it in one step. Let me do it in more steps. Tick, 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 tick. No, I I will do this. I will do it by part. Don't worry. I will do all of this, right? So first step, I will start with the one. Okay, the one is one, right? Like that, like that, like that, like that, like that, and like that. Then we shifted 4 times, right? So now 1, 2, 3, 4, it will be here, right? And all of these are these zeros, right? And here, I don't know what's happening, right? Because these are the bits that work here. I don't know what's up. Okay. Then we negate that. So now this is 1, 1, 1, 0. We don't know, we don't know, we don't know, we don't know, right? And then now I have all this number complete, right? Then I am doing an AND of the DDRD with this thing. What's happening there? It will be and x and 1, x, 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 0, then x and whatever, I don't know, right? 0 and whatever, 0, right? And I don't know, I don't know. What we achieve with this line? Now the second button is also an input, right? And with this, the only thing that I will be doing is change that to a 0. Is that clear? That's really easy, right? Now, let's just do one of these, okay? What is this? It's the atomic form of an OR. Yes? Okay, so what we are doing is I have a 1, I shifted 3 times, right? So that just means that I have 1, 1, 2, 3, something. Sorry, these should be unknowns. We can select. Okay. I should have a 1 there, 0, 0, 0, 0, and I don't know, I don't know, I don't know. And then I do the OR operation, right? What's x or 0? X. 0 or 0? 0, fine. X or 0? X. 0 or 0? 0. X or 1? 1. 0 or whatever thing? Yes, it's a whatever thing, but it shouldn't. Okay, let's imagine it's a 0. Yes. It's because, yes, in this case, they are, this is not my code, this is ChatGPT code. But he's, remember that I told you that normally these are 0? It's taking that in account, right? And it works, so it's true. But in reality, 0 plus this thing, it could be a 1, right? Let's suppose it's like that. And I don't know, right? Because they doesn't matter. So this line just make this a 1, because that's the first LED, right? And this will make this a 1, and this make this a 1, right? So right there, you are using different masks. Here, we are using the AND because I want to force zeros in some positions. In this, I am using the OR because I want to force 1 in some positions, right? And all of this in my code is just one line, right? But there are different ways to program, right? And here they have another things with the same. But is the atomic way to write things clear for you? Yes. So these are another way, right? If you see a symbol before the equal, it means this is the first element of whatever operation you have here, and the result is it's going to be saved in that same place, right? It applies for multiplication, division, bitwise operation, whatever operation you have. Okay. Any questions about that? Any questions about my questions of your homework? No, it's clear? Okay, perfect. Let me go to the presentation here. Okay. Now, the topic for today are analog signals, okay? So, in the last class, we used digital values, right? What does that mean? What does that mean? ones and zeros, right? We are codifying two different levels of something into values, zeros and ones. In our microcontroller, we are coding 5 volts as ones and 0 volts as zeros, right? In our microcontrollers, it will be 3.3 as ones, zeros are zeros. In PLCs, they use like 24 volts as ones or 12 volts as one, right? And you could also codify in digital form, for example, air pressure, right? In pneumatic systems, if you have pressure, you have a one. If you don't have pressure, it's a zero, right? So you can code whatever. In our Arduino, a logic one is whatever value greater than 2 volts, right? And zero is whatever value lower than 0.8. Those are the thresholds that you have to detect that. If you are in this zone, you can read whatever thing. It depends in the state of the microcontroller. So please don't send 1 volt there. You will not know what's happening. Okay? This is useful because maybe to our Arduino Uno we can connect a sensor of 3.3 volts, and you will detect the 3.3 as what? As 1, right? Because 3.3 volts right here. So for the Arduino, it's the same if you send 5 volts or 3.3 volts. But you have to be careful because if that sensor needs that you send some voltage to that, you cannot send 5 volts to the sensor. It will burn because it's 3.3 volts. So you can read without problem, right? It's a little problem, right? Normally, we use some circuits that allow us to communicate with that, right? And that transforms our 5 volt signal to 3.3 and transforms the 3.3 signal from the sensor to 5. That's the move. But if you are just reading something, you could do it with your 5 volts, even if the sensor of the element that you are connecting is 3.3 volts. Yes. Sorry? Digital. But it's also Boolean, logic. All of those are like synonyms for that, right? Are the same. Okay, so that signal is analog or digital? Why? Yes, because it's like 1 or 0, right? It's not in between. Okay, so that digital signal, those are the ones in our combo, right? We press the button, we send the 5 volts. We don't send like 3 volts and 2 volts. We send all the juice. Okay, in the other part, we have analog signals, right? For example, if in the Arduino Uno, we can read signals from 0 to 5 volts, every value in between, right? Not every value. We're going to study what's our resolution, right? But we can read a lot of values there. We can read, for example, 1.5, 3, 2.3, 3 point whatever. We can do that in some pins, not in all of them. They are all grouped in this part of the Arduino Uno. They are the analog inputs. In the code, you can reference them by A0, A1, A2, A3, A4, A5, right? That are the same names in the Atmega, right? In the Atmega, in reality, we have 2 more, but they are not present in the Arduino, okay? So if you program the Atmega, you have 2 more there. That in the Arduino, they are hidden because they are used for communication when you upload the program to them, right? But you have 6, okay? You cannot connect analog signals here. You can connect them, but maybe you will burn this or you are not reading anything, okay? Is that clear? Okay, now the microcontroller speaks binary. Everyone agrees on that? It just reads 0 or 1s. In the case of this, 0 or 5 volts. So how can the microcontroller read 2 volts? Or 1 volt? It just speaks binary. Anyone else? Okay. That is, how can the microcontroller produce right that? But how can you read? Yes, that's a good idea. Yes, we have some specific circuitry called. Anyone knows the name? They are called ADCs, analog to digital converters. Those are elements that takes our analog voltage and transform that to a binary number, as you said. But we don't have to use the power of the microcontroller for that. We have a specific module that is in charge to do that. Okay. There are several technologies to transform analog signal to digital signal. These are the five more important ones, right? The fastest is called flash. So it's really easy, right? In the test, if I ask you what's the fastest ADC transformer converter, you will have flash. Flash is the fastest, right? Okay. Perfect. Anyone knows what the one that is used in our Arduino? Successive approximation, right? So I will give you a brief explanation of this board, and then I will explain this with an example, right? The first one is called flash converter. They work in parallel, okay? And I will draw something, okay? I will try to explain with a little draw that I have to do here, not in the blackboard, here, okay. What's this thing? I have here a voltage source. Then I got one element here connected to ground, and I am reading here some voltage beyond. What's this? A voltage divider. Everyone knows this thing? This should be our best friend as mechatronics, okay? That's a voltage divider. If you connect two resistors in series, you can generate a fraction of whatever voltage you have there, right? So for example, if I have as an input voltage 5 volts, I can generate here whatever voltage value between 0 and 5 volts, right? Okay. We can also connect here a negative value. Right now it's not important, right? Anyone remembers the formula for a voltage divider? Almost the other way, yes. The output voltage is the input voltage times the resistor that is connected to the lower voltage. In this case, it's called R1. Maybe your formula is okay if I name the resistors the other way, right? Over R1 plus R2, the sum of both, right? The numerator should be always smaller than the denominator. That's always true because the denominator, I have the numerator, right? Plus something else, okay? If you have bad memory and you can't remember the formula for voltage divider, you can find it really quickly with Ohm's law. What's Ohm's law? Yes. Voltage equals to current times resistance, right? So the current flowing here, I will call that I, right? So I equals to what voltage? Being, right? Over what resistor? Both of them, right? R1 plus R2, right? Then, what's the current flowing across R1? I, right? The current flowing here is the same as the one flowing here, okay? That's equal to the voltage here, right? To be out. Yes? No? Okay, these two resistors are connected in series, right? So all the voltage in this big resistor generates this current, right? That's this formula, the one here. The second formula is just taking this part because this is not connected to anything, right? So all the current is here. So now the current flowing across the resistor R1 is the same current. I generates now this voltage, the voltage here, right? And I can substitute, for example, this in this one, right? So it will be V out equals to, instead of writing the I will write this thing, voltage input over R1 plus R2 times R1. That's this formula, right? It's the same. It's just grouped differently. Yes, so with Ohm's law, you should be able to remember the formula for a voltage divider. Is that clear? Because you will use that in your homework. Okay. Okay, voltage divider, you just connect two resistors, connect one to ground, the other one to another voltage. You can generate whatever fraction, changing the values of the resistor, right? Okay, now, this is introduction because we were talking about flash converters, right? That's top. Okay. Imagine that you have some voltage, input voltage, and you connect there several resistors. For this example, I will connect 5 of them. 3, 4, and 5. Connected to ground. Let's imagine the voltage input right now is 5 volts. In the Arduino Uno, normally we do the digital to analog conversion with 5 volts, right? That's the reason I am using 5. Let's imagine all the resistors have the same value. I will call that value R. It could be whatever, right? For example, here, if R1 and R2 are the same value, let's imagine 10 kilos, what will be the output voltage? Half of that, right? And if it was 5 ohms, also half of that, right? The value doesn't matter. Okay. What will be the value here of voltage? 0. Everyone agrees? Yes, it's connected to ground. It should be 0. Perfect. And here, 5 volts. And here, we could use the formula, right? What's the resistor below this? 4 Rs, right? Okay, 4 Rs over the total Rs, 5 Rs, right? Times the voltage. I can cancel this with this with this. That's 4 volts, right? Okay, and here, it will be 3R over 5 Rs times 5. Cancel, 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 cancel. 3 volts, right? Here, 2 volts. And here, 1 volt, right? I select, I cheat, right? Because I select the same value of voltage as the resistors. If I got 10 resistors, I can generate 0.5 volt, 1 volt, 1.5, whatever number. Yes. Yes, I am dividing the total voltage in the number.
Measure between both, you are making
Yes, for example, for this cable, I am doing a voltage divider between this thing and these things. For the 1 of 2 is because these are connected in series, right? Because right now I don't have any charge in any of these cables, so they don't exist, right? And if you take and you connect that in a protoboard and you can measure, you will get that, right? Right? This is the configuration that we use. It's called a resistor ladder because it's like a ladder, right? And we use that for a flash converter, right? The thing is that imagine I have here the voltage that I want to measure. It could be whatever voltage between 0 and 5 volts in this case, okay? And I will take that. That's my cable with that. And with this, I will connect this to a comparator. So I will compare that with 5 volts. Also that with 4 volts. Also that with 3 volts. And I will do the same for everyone, right? Anyone knows this little symbol? Right there. Yeah, very old, but it's like that. You know what's that? It's an op-amp, yes. Op-amp. It's an operational amplifier, right? It's a special circuit that does a lot of things. You are going to study that in 1 semester, I think. Okay? Right now, the thing that is important is that if this thing is greater than this thing, we will get here a 0. If the value here, in this case, let's imagine this is 3, right? Is 5 greater than 3? Yeah, 0. Okay. Is 4 greater than 3? Yes, 0. Is 3 greater than 3? 1. Okay. Is 2 greater than 3? No, 1. Like that, right? So whatever number, now we have a code in binary that we can send to our microcontroller, right? It's called in parallel because we are checking all the bits at the same time, right? We are running that in parallel. So this is really fast because we can do it in no time, right? Op-amps are really, really fast. We have the advantage, the disadvantage that is not so precise. To be very, very precise, I will need to have here a ladder of a lot of resistors, right? And if I have a lot of resistors, maybe the current flowing here will be very, very low and will be not enough to read, right? So we have a trade-off there, right? But we are really good doing semiconductors, so they work really well, right? The bad news is not the one in our Arduino. Okay, that's the first type of converter, right? It's important that you know that that exists. It's not so important because we are not going to use it, right? It's just so you have that exist and have a general knowledge of how it works. Yes. Yes, if this is greater than this will deliver a 0. If it's smaller, it will deliver a 1, right? And with that, we will have some change here, right? Right now, these increments are from 1 volt, so it's not so interesting. But if I have more increments, I can be really precise, right, in our measurement. The second one, it's called dual slope. Okay, anyone knows what's on slope? Pendiente and slope. Okay, this is an slope and slope, right? It's called like that because it works with RC circuits. What in reality we are just charging a capacitor, start charging. If we got to our correct value, for example, let's imagine I want to measure 3 volts, right? When it achieves the 3 volts, then we start discharging, and we measure how much time it takes to discharge, and that time is our number, right? So for example, if we count like this, it means that we charge very little, so the value is really small. If the counter achieves this number, it's a bigger value, right? And we have, it's proportional, right? Because the time is proportional to the resistance and the capacitance elements, and both of them are fixed. So the only thing that changed is the initial voltage that we got here, right? It's called dual slope because we start charging and then we discharge, right? We stop charging when we achieve the value of the reference, and then we measure the time, right? It's really precise. It's very, very precise. The disadvantage is that it's really, really slow because we have to charge the capacitor and then discharge. And if you want to measure again, charge, discharge. So it's really, really slow. Okay, that's the disadvantage. Yes.
Where is that used?
It's used in some elements. You can, have you worked with integrated circuits and not with the little like cartridges, black, to make circuits? No, okay. They are integrated circuits. If you want to transform an analog signal to a digital, you can buy an ADC, and maybe it uses this technology, right? They are used if your process is not so fast. So I will not be reading, for example, muscular signals because they are really fast, but maybe I can be reading the temperature of an oven. And doesn't change really quickly, so I can use that. They are really, really cheap. That's the other advantage of them. Yeah, because you could do yours with a capacitor and resistors and measuring how much time has passed, right? And they are really, really precise. Okay, successive approximations, I will explain that in more detail. Tracking servo, I will explain overall because there are a lot of technologies that achieve that. Imagine that you have your analog signal that you want to be reading, right? What the servo converter does, it tries to achieve the same value, right? So it starts increasing. When it gets, it will be trying to follow, right? If it decreases, it will start decreasing. And the ADC is generating the signal, so it knows the value and sends a binary value, right? This has some serious disadvantage. If the original signal changes really quickly, this cannot follow, right? So it's also not for fast signals, right? But this is how it works, right? And the last one works in the same way, the dynamic range. It tries to follow, but it doesn't follow linearly. It follows exponentially, so it can measure better the spikes, right? This is like a very wide family of converters, right? That's the reason I am not entering, because it's like a lot of technologies. I cannot explain one because they're really, really different. Okay. The important thing is flash are the fastest. It works with a ladder of resistors, and the successive approximation one, that is this one. Okay, these are the steps that the ADC follows, right? Yes. Yes. You can buy it. There is not in our Arduino, but you can buy one. They are slow. Is this dual slope? That's the name. It's called like that, dual slope. Yes. It's also called RC ADC because it uses charging and discharging of a capacitor, right? Okay, now this is the one for the Arduino, successive approximation. And these are the steps that it follows, right? And we are going to make a little example so you can see how it's working, right? In reality, you don't have to know how it's working because you just get the transformation of that, right? Let me just take a screenshot quickly so I can pass it to, okay. Let's put here, okay? Okay, so we have our Arduino, right? And we are going to reference or we are going to read values up to 5 volts, right? So let's start supposing that I have 5 volts. And I want to read one value. Tell me whatever number you want with decimal points between 0 and 5. 4.72. Oof, really precise. Okay, I want to read that, right? So we are going to follow this procedure, right? The ADC in the Arduino Uno is 10 bits. It means we can count up to what number with 10 bits? Yeah. 8 was 255, right? So 9 should be 512. And 10 it's 1024, right? So we can count from 0 up to 1023, okay? Because we have 10 bits. That's 2 to the 10 equals to 1024, right? Okay, including the 0, we have to subtract 1. Okay. We will start the code. Perfect. Then I have my 10 bits. I will start with my 10 bits. 3, 4, 5, 6, 7, 8, 9, 10. First step, clear all bits. What does that mean? What does clear means? Put all the bits to 0. Clear means reset the bits, right? Send it to 0. Okay, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, right? Perfect. Then begin with the MSB. Anyone knows what MSB stands for? Most significant bit, okay? MSB is the one in the left. And the one in the right, it's called LSB, least significant bit. Okay, how we know what is what? Imagine that I change this to a 1, right? What will be that number in decimal? A 1, perfect. And if I change this one, what will be that number? 512. I already know. Yes. This is 1, 2, 4, 8, 16, 32, 64, 128, 256. Yes. If you put 1 here and 0, 0, 0 is 512. If all of them are 1s, 1020. Yes. So if you change this, makes more change, right? It's the most significant. And the one there is the least significant. It's always like that, right? Okay, so let's erase this thing. Okay, clear all bits, perfect. Begin with the most significant one, okay? I will begin with that. Set bit, what does that mean? Set a bit means change it to 1, okay? Reset it, send it to 0. Clear or reset, send it to 0. Okay, I will start like that, okay? Then it's asking me, is the voltage generator greater than the one that you want to measure? Okay, to calculate this thing is just one thing. To calculate Vx equals to the number I generate, which is this number. 512, I already told you, right? Over the total number, what's the bigger number I can generate? 1023 times my reference voltage, 5 volts. Okay, that's equal to 2.5, right? That's my voltage. Is this greater than 4.73? No. Okay. Did I pass all the bits of the number? No, right? I am the first one. I have to move. Okay. Now I'm in the first one. Advance to the next bit. Okay. Now we are here in this bit. Set bit. Okay. I have to set it. It changed it to 1, right? Now, to transform that number, what's that number in decimal? That's 512 plus 256, right? Okay. 768. What's the result of this operation, please? The total? Three point? Okay. Yes. Is that greater than 473? No. Okay. So we advance to the next one, right? We set it. Okay. Now, what's that in decimal form? It's 78 plus 128, right? 1698, right? What's the result of this operation? Change this to 896. 4.37. Okay, is that bigger than the one that we want to measure? No. Okay, let's jump to the next one. Okay, we change that to 1. You select a really weird number. Okay, perfect. That's fine. I changed that to 1. What's that number in decimal? Is that plus 64, right? So that's 0, 1, 6, 960, right? What's the result of the operation, please? I hope now it's bigger. No? Oof, okay. It will start as that. Jump to the next one, right? Now it's a 1. That will be this plus 32. That's 992. No, right? Yes. Okay, finally. Is that bigger than this? Yes. Clear the bit. Okay, that means we go to 0, right? We finish all the bits? No, we go to the next one, we change to 1. I will not finish the 10 bits, right? The ADC does this, and the result of this is the corresponding binary number to the value that we want to measure, right? It's in the scale for the Arduino is between 0 volts and 5 volts. You will get a value of 0 and 1023, proportional to that. Yes?
Once you got the greater number, then like
you continue. We will continue. Now, for example, I clear this. You change that to 1, do the calculation. If it's greater, yes, and you continue for all of those. Because you will be like higher, lower, 1, 0, 1, 0, until you achieve a value really, really close to this.
It's like
Iteration, yes.
not like the next calculation that you make, it's not like
No, I will have to calculate the decimal of this. Oh, we can do it. Don't worry. Yes. It's whatever value we want to measure. For example, it could be a sensor of inclination, and it will give you some voltage. I want to read that. This is happening thousands of times per second. So you can be, if you are plotting this decimal number that you are getting every time, you can plot the voltage that you are reading. Yes, you have to transform this to decimal, right? This binary. So it will not be this thing. It will be up to here we have 960, right? And then you have to add up 16, okay? So that will be 972. Yes.
that in it's like a constant, the measurement will never be equal. Well, the division will never be the same as the voltage.
That will be our next slide. Yes, it will be really really approximate.
Never.
Never is a very hard word. Almost never. Yes. Yes, yes. No, but the number that you are converting is this binary number up to decimal. So
One,
110001. Yes, and that will represent a number between 0 and 1023, right? That corresponds to a specific.
yeah, like close.
Yes, it will be the closest possible. Yes. Yes. I will get this number, a number between 0 and 1023. That's an integer. And then you can do the operation to transform that to the voltage, right? Yes. And we have a function in Arduino called map that we can map it. Or you can just divide whatever number you get that over 1023 times 5, right? That's the conversion. It's just a rule of 3. Okay. Is the procedure clear? Yes, at the end you will get a number of 10 bits that allow us to read the analog signal, right? Not us, the microcontroller. Okay. Next slide. Now, every ADC from whatever technology has a resolution. To calculate the resolution, we use that formula, right? That is the reference voltage. In the example, we use 5 volts, right? 5 volts over 2 to the number of bits minus 1. Okay, so in the case that we were doing, we have 5, 2 to the 10 was 1024 minus 1, 1023. That's equal to 0.0048 volts. That means that the resolution for the ADC in the Arduino Uno is 5 millis, right? 5 millivolts, almost like that. So we cannot read increments or decrements that are lower than that. But I think that's good enough, right? We can read 10 times half a volt, 100 times half a volt. But yes, how can we increase the resolution? Increase the resolution means making this number smaller, right? How can we increase that? Yeah. What happens if I reduce the reference voltage? Instead of using 5, I use 1. It will increase, right? Okay. And if I increase the number of bits, which one increases the resolution faster? This one, right? Because it's an exponent. So one more bit will give you a lot more resolution, right? In reality, if the resolution of your microcontroller is not good enough, one option is use another microcontroller. Right now, there are microcontrollers really, really cheap with ADC converters of 20 bits. So you have a really, really high resolution, right? Or the other thing that you can do is you can buy the ADC module and connect that to your microcontroller, right? There are ADC modules that can communicate in different ways to the microcontroller.
The bigger is
Bigger resolution means that that number is smaller, right? Okay. Okay. In the Arduino, all the when you are reading the analog value, it takes just 100 microseconds, right? So it's not so fast as the flash ADC, but it's really, really fast, right? Because here we can read the 8 channels in the Atmega in that speed. So it's really, really fast, right? It's not so fast, so make an oscilloscope with this, but it's really, really fast, right? There are microcontrollers that you can use to buy your own oscilloscope. But this you can use to read signals that are not changing so fast. The rate is 10,000 times per second. A lot. Okay. To read an analog signal, we use analog read. To read a digital signal, we used digital read, right? The syntax is the same, just that you you just have to use the ones that you can use that are A0, A1, A2, A3, A4, and A5, right? In an Arduino. And that, if you don't write this expression, you will use as a reference 5 volts, right? Or you can write this expression, use the fault, expression is another reference, use the fault, and you will be using 5 volts as reference for the conversion, right? You will have the resolution of 5 millis. Or you can change this to internal, and he will use some voltage, some internal voltage that is 1.1. So now you will have a resolution of 1 milli, right? If with 5 volts you have 5 millis, with 1 you have 1 milli. So you will increase the resolution. What are you losing? That now you cannot read voltage values greater than 1.1, right? Because you will burn the circuit. Okay. But if you need to read little signals, for example, electroencephalographic signals, you know the signals are really, really small. So you can use this thing, right? And we have a third option, that is to connect an external reference, right? So you can connect whatever voltage you need to generate your conversion, right? 3 volts, 2 volts. To do that, you have to connect your reference voltage to this pin. To a pin here, it's called a ref. If you remember in Proteus, we were connecting that to 5 volts, right? It's because we use that. But if you have a specific sensor that delivers a voltage between 0 and 2.1, okay, you could connect there 2.1, and you use all your ADC conversion right there. So you will be more exact. Okay, we were there. Okay. You know what's a potentiometer? What is a potentiometer? It's a variable resistor, right? They are linear ones. These ones are rotational ones. They look like this. We have 3 inputs that they are smaller. We have different ways, right? Well, these are the most common. They are a resistance that we can change its value, right? It has a fixed value. It's like this. For example, this is a 5K one. You can have a 100K, whatever, right? This is schematic of its internals. It's just a resistance that is connecting these two terminals, right? So, for example, if this is a 10K potentiometer, what do I measure if I connect the multimeter here and here? 10K, perfect. And if I move the wiper and I measure again, 10K, right? Because this is fixed always, right? This terminal is called the wiper, right? Because this is the wiper, right? Moving across that. Imagine that the wiper is right here, okay? What will be the resistance if I measure here? Almost zero, right? Because the current will be flowing here. It's zero. But if I measure from here to there, I will have the 10K, right? If I got here the wiper and I measure from here to there, 5, and from here to there, 5 also, right? The sum of this plus this is fixed, right? It's the value of the potential. And I can generate whatever value I want, right? What happens if I connect here ground, here voltage? And I measure here the voltage from here to there. It's our voltage divider, no? Because we have two resistances. So it's the same as this thing, right? This is our potentiometer. And in the formula, this would be the fixed value of the potentiometer. And I can generate whatever value there, right? So I can connect a potentiometer to an analog port and generate whatever voltage value I need, right? To read it. Okay. Finally, analog output, right? Now I know I can read analog signals. I can also write pseudo-analog signals, okay? I can write those in the pins in the Arduino that has the little wavy line. Do you remember which pins are those? You have your Arduino there? We have 6 of those. No, I think they are 3, 5, 6, 9, 10, 11. They have this little symbol, right? They are capable to work as analog outputs. It works with PWM. Anyone knows what's PWM? pulse width modulation, right? That's the meaning. It means that we have some signal, right? Let's imagine here I have a periodic signal. A periodic signal means it's a signal that repeats itself, right? Several times. It will be repeating. The only thing that remains unchanged in a PWM signal is the period of the signal, right? Is the size of the cycle in time. So, for example, for the Arduino Uno, it has a frequency of 500 hertz, right? It means that the period is 1/500. That's what? 2 milliseconds, right? Okay. And maybe it's not that. You can do the division, right? Okay. And with that signal, imagine that I maintain the signal in the high value all the time. What will be the voltage value of that? 5 volts, right? Okay. If I maintain the signal all the time low, 0, perfect. What happens if I maintain as it is, half of the time up and half down? What's the mean value of that? 2.5, right? Okay. We are changing this between 5, 0, 5, 0. It's digital, right? But we are changing so fast that we can deceive our elements, right? If I connect this to an LED, I can change the brightness because I can generate fractions of the voltage, right? If I connect a motor, I can change the voltage, so I can change the speed, right? The speed of a motor is proportional to the voltage that we are giving to that. For example, if I put 1/4 of the time up and 3/4 down, how many voltage do I generate? 1.25, right? It's 1/4 of the 5 volts, right? Okay, in the Arduino Uno, our converter, our PWM converter, it's 8 bits. So we can convert 256 values, right? So we can divide the 5 volts in 255 equal values, right? I can generate whatever value in that signal, right? To send that in the Arduino, we are just going to use, for digital one, we use digital write. For the analog one, we are going to use analog write. We just tell the pin. It can be just these pins, 3, 5, 6, 9, 10, 11. I think I got it right. Okay. And then the value. The value is the number between 0 and 255. If I send 255, I will be sending 5 volts. If I send 128, I will be sending 2.5 volts, right? Half of that. If I send a 0, 0 volts, right? So I can send whatever fraction there, right? We have homework in Canvas, but we are not going to do because I want to explain a little more before you deliver that, right? So I will leave that if you want to pick and start watching that, but don't obey the date, right? It will be for later, right? It will be like that. There's no homework for Monday, just to bring your advances in the challenge. Did you finish? Also to bring the other, okay? Okay, any questions? Okay, so see you on Monday. I will show you some examples of this, and then we are going to see another topic, right? Bye, bye, bye. Thank you.